Hello guys, welcome back. Dr. Mandis here, talking today about more about electrochemistry, in this case, electrochemical potential. Electrochemical potential, just potential or electrochemical reduction potential. Typically, we just say potential. Basically, there's an easy way to understand it, and there's more complicated. And another post on spontaneity, I do the more complicated. Right now, we're going to say, look, the potential is best explained. Think of it as a likelihood. And like, you have potential to succeed. If our Martian dude has a potential of, I don't know, 8 and to win $1 million, where the Smurfy guy or girl, okay, has a potential of 2 to win the same $1 million, who do you think has a greater potential? 8 versus 2, right? More likely, less likely. Cool. What if instead of 8, it was a -8? Probably not, you know, probably now, hey, 2 has the greater potential, greater likelihood of winning the $1 million. Okay, what if a -8? Ah, -2. Probably neither one has a really solid potential since they're both negative. Okay, but -2 beats -8. So he would have the greater potential, although it's not bloody likely. Okay, voltages are potential differences for current flow. All right, when we look at half reactions and we have our groovy little half cells set up, and you got the wonderful little wire and electrons flowing through there creating current, there's a voltage. Okay, and that's why these are in voltages. Okay, if you look at the two, but its voltage is a potential, which is why these guys are potentials. All right, so if you look at the first one, we have a potential of -0.76. If you look at the second one, also a negative potential, but it's bigger than the other one. All right, -0.036 is actually more than 0.76. Remember number line, man. 0 on up. These are negative, those are positive. The more you go this way, the bigger you are. Well, -0.36 is bigger. Okay, so pay attention to that negative. All right, a lot of students tend to overlook it. So anyway, as far as this goes, let me get rid of some of that. All right, you have two potentials, and one is bigger, one is smaller. This guy is the smaller potential, okay? These are redox reactions. They're half reactions, but it's redox, which means we need an oxidation and a reduction. They're both written for reductions. He's got the better potential, so odds are he's going to stay reduced. This one has to flip and become oxidized. So what we do is we flip the equation. Zinc goes to zinc 2 positive plus 2E negative. If we flip the equation, just like with delta H's and delta G's and delta S's, when we flip it, we change the sign. It's now running in the other direction, so the sign changes. So instead of negative, it's going to be positive. Cool. When you go to when you go to add up the half reactions, just like under Hess's law, we added all our delta H's, we just add them up. Okay, 0.76 plus -0.036 with 2 decimal places there because sig figs, 0.72 volts. All right. Over here, when we go to add it up, you got an issue. You have 2 electrons. Whoops, wrong color there, Dr. Mandis. When you have, I'll talk to myself. 2 electrons there, 3 electrons over there. They don't cancel. We need to cancel electrons, just like we always do when we add up redox reactions. We're going to multiply this whole thing by 2. Multiply this whole thing by 3, so that we have 6 electrons here, 6 electrons there, and they cancel. So really, it's not going to be iron. It's going to be 2 irons and 2 irons. It's going to be 3 zinc and 3 zinc 2s. Cool. And they'll balance. The reason we don't multiply this stuff is complicated, but it's kind of like mass versus density. Okay, if you double the size of something, you change the mass. Like a cup of water, a gallon of water, you're changing the mass. You got more. I know I'm talking in volumes, but you get the idea. If you think of a cup of water, a gallon of water, the density of water is constant in there. The density of water is not changing. It is an intensive property. Well, electrochemical potentials don't change. They are the potential for each time the reaction occurs. This side never gets multiplied by the 3 and the 2. Okay. If you are someone that goes online, looks up a lot of stuff, or you're a purist, the electrochemical potential of a reaction, this gig, is actually calculated by a lot of places as the reduced minus the oxidized. And all they're doing there by running it that way is they're incorporating the negative here and just saying add up the numbers but subtract them. I don't like that because you already know how to do this. You already know that if it flips, the sign changes. Since you already know that, change the sign, and you're already familiar with this stacking them up and adding them gig from Hess's law, so stack them up and add them. But if you really, really, really want to do that, cool, go to town. Let's look up a couple of examples of these kind of fast because I'm rambling here. Right, the overall balanced chemical equation, calculate the potential. If you are given these two half reactions, okay, he is definitely the smaller potential, so we're going to have to flip him. And that's why I said he's lower, we're going to flip him. And that creates the flip. And so he was positive over here, he's now negative over here. So we're just going to add these guys up. Dink, dink, dink. All right, and you get plus 1.34. That's what happens when you copy and paste. Over here, we need to multiply through to cancel out the electrons. And so this gets tripled, and so we have 3 coppers, but the gold does not. Notice again, we did not multiply here by 3. That's a no-no. Cool. So the other way to do this is, what if you're given the overall equation, and then you're asked to calculate that? If you're given the overall equation, you kind of got to go backwards through all this. And so I did one of those here for you. Okay, permanganate plus iodide, I'm right here. Permanganate and iodide to make manganese 2 and iodine. The cool thing is you're going to look up the electrochemical potentials in the table. They're in your textbook, they're online. When you look them up in the table, you're going to get the balanced half reaction. You won't see one that just has MnO4 and Mn2 positive. It's going to balance it for you, which is cool because then you don't have to. So that's nice. All right. So anyway, so I get my 2 half reactions here. All right. I'm looking at them. I wrote this out here for you. All right. If you look here, okay, and permanganate to manganese 2 is a loss of 5 electrons. Iodide to iodine is a gain of 1 electron per iodide. Okay, that's why I doubled it here for 2. All right, so manganese is being reduced. The number is going down from 7. Number is going down from 7 to 2. That's a reduction, the loss of 5 electrons. So that electrochemical potential should be as written from the table. Iodine, however, is going up. That's an oxidation. So when you look it up in the table, it's going to give you a number because this reaction will be backwards. This one will be backwards of what it is. It'll be written as a reduction. So then you have to flip the sign. And so I did flip the sign. Okay. And that made it negative 0.454. You then add them up just like you did before, 0.95. Just students often can't say, I couldn't find this one, I could only find the reverse, because they're reduction potentials. All the half reactions are written for reductions. If you need an oxidation, you have to flip it, which again flips the sign. We talked about spontaneity a little bit earlier. Well, I didn't talk about it specifically. If it's a positive likelihood, then it should happen. That's the definition of spontaneous. If it's a negative likelihood, not likely to happen, that's the definition of non-spontaneous. More to follow in a video on spontaneity, but for right now, I think that'll be good. Hopefully you learned it. Have a good time, like this up, and I will definitely have to talk to you later now. Take care.